Okay, so here we're going to try to approximate 2.03 raised to the third power by hand, no calculator, just using differentials. And differentials are going to help us do this. If you recall, differentials kind of came from the idea of approximating a function using a tangent line, and differentials were those changes in y and changes in x as you move from the point of tangency to other places locally around the point of tangency. So without going through a lot of detail, what we saw was that if you want to evaluate a function at a place that's an ugly x value, which is x plus some change in x, where x is a nice x value, maybe like 2, like it would be better if that 0.03 wasn't there. We would rather do 2 cubed, not 2.03 cubed, but evaluated at x plus some change in x, in this case 0.03. And it turns out to evaluate that function at the ugly x value, like 2.03, what you can do is just simply take the y value at the nice x value, like 2, and then add in what I like to call this corrective factor, this fine-tuning factor that gets you exactly or close to the y value at 2.03 cubed. Rather than just 2 cubed. So anyway, first of all, let's just kind of pick out who's who. Who is the function? What's being done to this number here? Well, I think x cubed would be the appropriate function because we're cubing 2.03. Now, what is your quote-unquote nice x value around 2.03? Well, obviously it would just be the 2. Now, what would that make the delta x, or the change in x, away from 2? Well, in this case, it's pretty clear that it's 0.03. So we're going to take these things, and oh, by the way, I forgot. Let me get the derivative while I'm at it. The derivative of x cubed would be 3x squared. So now that I have these things, let me take them all, and we'll stick them in and see what we get. All right, so f of x plus delta x, that'll be 2.03 cubed. That's the y value at this ugly x coordinate. And this should be approximately the same as just 2 cubed. And that makes sense. 2.03 cubed is probably pretty darn close to 2 cubed. But then you have to add in this corrective factor that fine-tunes it to be more accurate. So I'll take the derivative evaluated at 2, not 2.03, but 2, the nice value, which would be 3x squared, but instead of the x, I'll pop in a 2, times the change in x, and the change in x was 0.03, 0.03. All right, do a little algebra. 2 cubed is 8, plus 2 squared is 4, 4 times 3 is 12, 12 times 0.03. So 12 times 0.03 would be 0.36 if my algebra is right. And so this should be roughly 8.36. Now, in just a second, we can take this. Matter of fact, let's just go ahead and do it right now. We'll take 2.03 cubed, and we'll see what the actual quantity is. So 8.36, this is the approximation. And notice I did this no calculator. This was only using differentials. Let's go to our calculator now. And we'll take 2.03 raised to the third, and let's see how good we did. All right, let me cut this out and compare it to the answer we got. Paste it over here. Okay, the actual y value, this is the perfect y value, is 8.365427. So is our approximation pretty good? Yeah, I'd say so. I'd say it's great, in fact. I just find it very, very cool that we can find the y value, or approximate the y value for such a crazy quantity, for such an ugly function at an ugly x value by hand, no calculator, just using these differentials, these changes in y and changes in x.